All right, 20-1s. Let's take a second look at piecewise, which comes from absolute functions. So I realize this is video 2. Some of you might have just done lesson 1 with this, but an absolute function. Remember, if we have a function, y is equal to f of x, well, we can come up possibly with a second function where we want the absolute of that same function. Now, as a quick review, our initial function, if I just take a look in terms of a quick sketch, if I had some type, maybe it's just a line, there you go. That's y equal f of x. There's our function, and there's our graph of it. Well, the absolute, if I want to now graph the absolute of that same function, well, what happens? Because it's the absolute, our y values are absoluted, so all the y values have to be positive. So all of this portion here of the graph where we're into y values that are negative, well, our absolute graph would take all of those values and reflect them so they become positive values. So this point here, whatever it was at, let's say it was at y negative 2, well, it's now at y positive 2. And if we had this point here, which is at y negative 4 maybe, well, it's now going to be reflected to be at y positive 4. So we then have our y equal to the absolute f of x, where part of the graph stays the same, but all of this negative portion has to be reflected up so that all the y values are now positive. The initial f of x graph, just a regular graph, line graph, but then we end up with the absolute graph where part of it's the same, but that negative part reflects up and all the y values become positive values. The negative y values become positive y values. That's what an absolute function graph does. Technically, we don't even have to be able to know what the function is. Again, if I took something that was totally goofy, a graph that we haven't even looked at before, let's say that's the graph. This will be maybe in 30-1. You'll get a graph like this. But if that's your y equals f of x graph, well, we know that if we want the absolute for that graph, that's going to take all of these negative y values and have to make them positive, because that's what an absolute does. Y has to be everything positive. So that means this portion of the graph where y is negative, it would now have to become positive. Whatever this point was at as a negative, let's say it's negative 5, well, it's now going to be at positive 5. The part that's already in the positive, it'll stay the same. This is positive y, it'll stay the same. But again, this negative y section would reflect, and this point here, whatever it was, let's say it's negative 9, well, it's now going to become positive 9, so that our negative portion of the graph becomes positive portion. So this in blue would be our absolute f of x graph, because everything's positive. But the initial just f of x graph would be able to have positive and negative. So some of the graph, the invariant points are the same. Those points are the same, but some of the graph reflects. And piecewise is going to, remember, identify what parts of the graph where the domain takes us to the normal and the absolute part of the graph. So let's walk through another example. Let's take a look, page 7 of the booklets. And we have the equation y absolute 3x plus 1. Well, the first thing is I want to know, what does our y equal to 3x plus 1 graph look like? Well, we go back to grade 10. There's our y equals mx plus b. So our y-intercept is at 1. And our slope is at 3, which we could write as 3 over 1. So we know every point is going to have to be positive 3. 3 up, 1 to the right. 3 up, 1 to the right. Or 2 negatives down and left will also give us points on that line. So there's our y equals 3x plus 1 graph. So at that point, we want the absolute graph. So we want y equals 3x plus 1. Now, basically what I'm doing here is I'm using the information from grade 10 instead of using the table of values. Table of values will get us the same thing, but it's not totally necessary. So at this point, what do I need in order to get the absolute graph? Well, I know that my absolute graph means that all of these points where y is negative have to become y positive. So this negative 2 y value is going to become a positive 2. This negative 5 y value is going to reflect and be positive 5. So my new graph, I'm happy with that part of the graph. Go down to the x-axis, and then we bounce up. And there's the y equals absolute 3x plus 1. Half of the 3x plus 1 graph stays the same, but half of it essentially has to reflect to keep our y's positive. So there's what the absolute graph looks like. Now, what was important, the key part, is the x-intercept. Because the x-intercept, remember, is our bounce point. X-intercept, it looks like, is about there. So if I calculate the x-intercept, just for the regular function, x-intercept means y is 0. If I solve, I subtract 1, divide by 3, and x works out to be negative 1/3. So our x-intercept is at negative 1/3, 0. And if I find that point on my graph, negative 1/3 to the left, 0. It's not absolutely perfect because I'm just doing a quick sketch, but we see our bounce point is at negative 1/3, 0. That helps us come up with piecewise. Because with piecewise, we need to identify where does the normal function y equals 3x plus 1 occur. It occurs if, and that's where we need to identify our domain, because that's what piecewise is. Here's the normal. All those points stayed the same. That occurred from negative 1/3 and up. So our normal graph occurs if x is greater than or equal to negative 1/3. But we also have the absolute part of the graph, which, remember, we identify with that negative. That identifies we need to reflect. So the absolute part of the graph occurred. Where did the absolute part occur? Well, the absolute part of the graph occurred for everything smaller than negative 1/3. So the absolute portion of the graph occurs when x is less than negative 1/3. And we can't have the equal to on both of these. We always put it with the normal graph, essentially. So there's the piecewise for this. We get our absolute graph. The normal part occurs from negative 1/3 and up. The absoluted part of the graph occurs from negative 1/3 down. Take a look at one more example, page 9. And now we're looking at x squared minus x minus 2, the absolute, which is a parabola. So with our parabola, I want to graph to start with y equal to x squared minus x minus 2. Well, in order to come up with this parabola, we need the x-intercepts, because the x-intercepts help us to create the parabola. So x-intercepts, y equals 0. And now I get my x-intercepts. How do I get x-intercepts? Solve for x. I can factor, multiply to negative 2, add to negative 1, x minus 2, x plus 1. So our x would be positive 2 and negative 1. So we know at positive 2 and negative 1, our x-intercept, that's on both our parabolas, and those will be our bounce points. But how can I sketch a parabola? Well, the easiest way is to convert to vertex form so we can get a vertex. Here we go. Y equals x squared minus x minus 2. First thing, bracket your x squared and your x. We want to have x squared and x, so we actually have to factor out a 1 here, which does nothing. And we're left with x squared minus x, and we're going to have to put in that extra value. That special magic value, remember there's a negative 1 there. We want negative 1 divided by 2, and then we want to square that. So that's what we have to look at doing. So when I do that work, negative 1/2 squared is positive 1/4. Well, what did we add to this? We added in 1/4, but I don't want that 1/4 in there, so we're going to subtract 1/4. We need the 1/4 as part of the function, but I don't want that 1/4 value added in, so we subtract 1/4 because now we've added a value of nothing. Finish off by factoring what's in the brackets, and remember, what's in our magic is what it is. What are the things that multiply to give us 1/4, but add to give us negative 1? Negative 1/2, negative 1/2. Negative 1/2 times negative 1/2 is 1/4. Negative 1/2 plus negative 1/2 is negative 1. So we end up with x minus 1/2 squared minus 2 1/4. So now we have our vertex is at 1/2 negative 2 1/4. There's where our vertex is at. So to keep going from there, we need at 1/2 and negative 2 1/4, and it's not going to be perfect but we can get an idea. All right, there it is. There's our vertex. It's a positive a value 1, so we know what it opens up, and we have 2 points on it, our x-intercepts. So there's our y equals x squared minus x minus 2. But we now need the absolute of that graph. We need the absolute of x squared minus x minus 2. Well, that means this negative y portion needs to reflect up. So our vertex, instead of being down at negative 2 1/4, it needs to be up at positive 2 1/4. So it would be about there. We still like this portion of the graph. There's our bounce point. We don't go into the negative y's. Don't go into the negative. And there's the absolute of x squared minus x minus 2. So now we need the piecewise. Our regular graph, x squared minus x minus 2, y will equal that if what x values tell us and give us the normal part of the graph. There's the normal part of the graph, the invariant points that don't change. That happened for x values bigger than 2, and that graph also, normal part happened for x values less than -1. So we'll have y equals x squared minus x minus 2 if x is greater than or equal to 2, and if x is less than or equal to -1. But we also have the second part of that graph, the absolute part, which is identified with that negative out front because we've reciprocated. And where does that happen? Well, that portion happens here. There's where we get the absolute part of the graph, the part that had to change. And it happened from -1 and up, but from 2 and down, all those points. So we write that as a domain saying from -1, we want that to be less than x, and x also has to be less than 2. There's our piecewise. It identifies what parts of the graph, or what part of the domain, the x-axis, gives us the normal part of the graph, and what part of the x-axis gives us the absolute part of the graph. Hopefully those two examples help you solidify piecewise a bit. It's a quirky little concept. It takes a lot of time to get it down. It's not totally essential, but it's important. Make sure you're on top of it. So again, there's the assignment from the last video. Plug away. Have fun with it.